The video for today is going to show this diagram and how water heats from a solid all the way to a gas. So in this case, you're going to see heat going higher on the bottom from left to right and temperature going higher from bottom to top. What we're going to look at is a 100 gram sample that will just make the math a little easier. And we're going to start at a temperature below freezing and go to a temperature above boiling. So you're going to have 5 different segments of this chart where we melt the ice, change the phase, heat the water, change the phase, and heat the gas. It sounds complicated, but there's really only 2 equations that we use. We just have to use them in the right order. So I'm going to start off with remembering that our thermal energy equation, Q equals mc delta T. In the case for ice, which we haven't done yet, C equals 2.1 joules per gram degree Celsius. So when I apply the formula, 100 grams, 2.1 joules per gram degree Celsius, and 30 degrees C, because we're going to say, for argument's sake, that the ice is 30 degrees below zero in the Celsius system. So we end up with, we end up with a thermal energy added of 6,300 joules. That gets us from negative 30 C to zero, where we're still frozen, but we're and ice. We haven't switched any to water yet. The next slide takes us to the phase change. And we talked a little about this latent heat of fusion, but we didn't actually apply it to a problem yet. So here we are. We're going to take that same 100 grams, and this time we're just going to multiply it by what we call the latent heat of fusion, which is 334 joules per gram. Now, if you note in this formula, there is no delta T because there is no change in temperature. This mixture of ice and water will stay at 0 C until all the ice is gone. And with 100 grams, the math is easy. We just end up with 33,400 joules to change the phase completely from solid to liquid. Now, the next problem is one we've practiced in class. We've actually done this exact problem, and I just put it up here to remind you that for water, C is 4.2 joules per gram degree Celsius, and we end up with 42,000 joules to take it all the way from freezing to boiling. The phase change at 100 degrees C is actually a little bit more energetic. You'll recall the latent heat of fusion was 334 joules per gram. The latent heat of vaporization is 2,260 joules per gram. So it takes a lot more energy to vaporize water into steam than it does to melt ice into water. And so the math is before you, and you can see how that problem works out. And you see where the energy lies in this, 226,000 joules. Now the last part is, I'm going to arbitrarily say we're going to continue to heat the water from 100 grams, or from 100 C up to 145 C. I just had to pick a number where we're going to stop. But note for steam, the specific heat is different again. It's 2.0 joules per gram degree Celsius. So we do the math and we find out that we have 9,000 joules of energy required to heat the water up that 45 degrees Celsius. The last slide that I'm going to show you is I put those numbers on the chart so you can see where the energy was put in the most. It's clear that it takes far more energy to steam water out than it does to do any of the other things that we did. Going all the way from negative 30 Celsius to 145 Celsius takes a total energy of 316,700 joules. And roughly 2/3 of that is just for the steam transition, going from water into steam. So I'm going to give you this video, and then I'm going to attach a problem similar to this to your to the assignment on Teams, and you can do that problem and again submit it to me by just writing it down on any piece of paper and sending me a picture of that in the assignment on Teams.